I'm excited to be here today and present to everybody in the company regarding the Goleta nanobubble pretreatment pilot. So with that, I'll get started. So in wastewater treatment plants, a new problem that we're having is the concentrations of QACs and surfactants. These are present in both municipal and industrial waste, and it's one of the main inhibitors to a biological wastewater treatment process. Quaternary ammonium compounds and surfactants, they contribute to the loading of the treatment plant. They reduce oxygen transfer, which wastewater treatment plants, that is our primary treatment method. They emulsify contaminants in water. They decrease the ability to remove water from our sludge at the end of the process. Overall, QACs and surfactants are kind of working against the natural processes that we use in wastewater treatment plant. So the source of the surfactants are primarily from consumer products that we have. They can be industrial in nature too, but when you think about your daily life, you have hand soap, laundry detergent, dishwasher detergents, degreasers in the kitchen or automotive parts, personal care products, shampoos, body wash, and then our cleaning and disinfecting products. Pretty much all of these products are common in that they are all different types of surfactants. They have different charges. Some are positive, some are negative, some have both charges. But either way, these products all have a purpose, and that is to use water as a solvent to remove some other type of contaminant. So they're always trying to keep our contaminants within water. So all of those chemicals have been around for quite a while. And so the question always is, well, what's changed? And so across California and most of the Southwest, the major change has been the amount of water that we're using every single day. And this has been really exacerbated by drought. We've always wanted to be more efficient with how we use water resources. It's one of the largest uses of energy in California, but the droughts that we've had over the years have made things much worse. Every single time we have a drought, there are new conservation measures. So back in the 90s, it was low flow toilets, low flow sinks. And so there was one level of conservation that occurred. Some of those things people fell back on when water resources were available. Most people probably switched their shower heads back to a normal one because low flow ones aren't that great. But after multiple years and multiple droughts, other major appliances have been changed out. Washing machines, dishwashers. We're going from hundreds of gallons down to 20 gallons per load of laundry and even less on dishwashers. So in a lot of these changes, when you spend that much money on an appliance, people aren't, going back after the drought's over. So a couple of the effects that happen for wastewater treatment plants due to these lower flows and higher concentration of waste is that we have a lot of time. It takes a lot more time for waste to get from people's households to the wastewater treatment plant. And this causes fermentation, anaerobic digestion of the waste. Ultimately, what that means is that the waste is becoming more difficult to treat. Fresh waste is always easier. So what are nanobubbles? They're extremely small. They're 2,500 times smaller than a grain of salt. And because of their size, they have some very unique properties that are different than any other bubbles. Some of these are that they lack buoyancy, they have random motion, and they have different charges. So the fundamentals of nanobubbles, they're hydrophobic, they have charged surface, extremely high internal pressure, hard shell-like surface, high gas transfer efficiency, and the behaviors are new, and these are what are very important to wastewater treatment, is that they're neutrally buoyant, stable and long-lasting, oxidative, electrochemically active, and they reduce surface tension. So surfactants interact with nanobubbles because of those properties and to their size. So nanobubbles are actually, their hydrophobic properties are competing with the hydrophobic space that surfactants want to occupy. And so the selection that we see in wastewater treatment is that our nanobubbles and the surfactants kind of want to occupy the same space. And because of their charges, they're attracted to each other. And so the theory is that when nanobubbles and surfactants come together, the nanobubble becomes destabilized and collapses. And the collapse of the nanobubble produces a reactive oxygen species that we call the hydroxyl radical. When this happens, long chains, and usually what we would call the tail of the surfactant, is going to be broken down into something that is shorter and more readily removed from the wastewater stream. So with that, the surfactants themselves are part of a measure in the wastewater that we call COD, or chemical oxygen demand. There are different types of COD, and this basically is how we measure the loading to wastewater treatment plant. Some of the COD is particulate and can be removed in separation processes, either by filtration or sedimentation, flotation. Other types of COD are soluble, like surfactants. One of the benefits to nanobubbles is that by breaking down these otherwise long chains of a surfactant, we're converting them from a slowly biodegradable form to something that's readily degradable and can be removed in the wastewater treatment process. So after a little overview on how nanobubbles are working as pretreatment in wastewater treatment plants, I'll go on to the full-scale demonstration at Goleta. So Goleta Sanitary has a design flow of 9.5 MGD. Their current average dry weather flow is 4.2 MGD, less than half of design, and yet they are fully loaded. So populations have increased, but the amount of water coming into the treatment plant has continued to either hold the same or decrease. So this plant is actually at its design capacity when it comes to contaminant loading. So Goleta's been aware of the impacts of surfactants since 2016, when they were having periodic upsets that were determined to be from periodic discharge from the airport across the street. When you're on an airplane, the toilets that you're using don't flush with water. Instead, they use chemicals to stabilize the waste and reduce odors. Those chemicals are in that class of surfactant that I talked about earlier. So a point source was really easy to identify and eliminate from the wastewater treatment plant, and we found a few others, got rid of those, and plant was healthy again. The periodic upsets went away. Unfortunately, 2019, end of 2019 into 2020 was the start of the pandemic, and this provided a new challenge with extra hand washing, extra soap use, extra disinfectant use, these periodic upsets of the wastewater treatment plant increased again. To make sure that it wasn't an industrial source, we did a lot of sampling from different places coming into the wastewater treatment plant, and we found that it was consistent from every different direction coming in. And so we concluded that it was consumer products. This was kind of a scary thing for me as a plant manager, because there's no technology widely available to deal with these surfactants at a wastewater treatment plant, and treat millions of gallons. So one day, I actually found a case study regarding the Fallbrook pretreatment with nanobubbles, and I said this must be the solution that I need. So in March, I contacted Moleaer, and we started the pilot project May 10th. So for those of you that are not familiar with wastewater treatment, there are a few major steps that are consistent amongst most municipal wastewater treatment plants. First, we have preliminary treatment. This is where we want to remove things that really shouldn't belong in the sewer anyways. So we use physical screening to remove plastics and large objects, things that will plug or damage our pumps downstream. Next, we remove grit. This is fine grit and sand that would be abrasive and do damage, once again, to the pumps downstream. The first process in most conventional wastewater treatment plants is primary sedimentation. This is where we use the relative specific gravities of the contaminants to either have them float to the surface or to sink to the bottom, and we remove those contaminants. After that, we have to go to a biological treatment process, and we use bacteria that consumes soluble contaminants within the water, and they use those contaminants as the building blocks to their own growth. And so we're taking things that are soluble and putting them into biomass. At Goleta, they have two different types of process, biological treatment process. The first one uses a media for the biofilm to grow on. So basically a lot of surface area, and they're spreading water over that surface area. The biology can attach to it. In between the water being spread, there's a lot of time for oxygen to come into the biomass. Once again, that oxygen transfer component is really important to wastewater treatment. The second biological treatment process that Goleta has is what they would call a suspended growth process. And this is very commonly known as activated sludge and is the most common wastewater treatment process in the United States. This is where we actually bubble air up through liquid containing the biomass. Next part of the process is we have to remove that biomass. So we took everything that was soluble, not removable, added it to the biomass, and then separated out in another clarifier. And later on in the presentation, you'll see how this biomass settles out, leaving clean water behind. Last step in most conventional wastewater treatment is that if the water is used for recreation, it needs to be disinfected. So Goleta's water goes to an outfall out to the Pacific Ocean, and therefore we disinfect the water with chlorine bleach and then remove the disinfectant with sodium bisulfite to prevent any fish kills or any problems. Goleta also has tertiary treatment where they recycle water for irrigation use. And this was actually where our primary concern is that due to the concentrations coming into the treatment plant and the loadings and the difficulty in treating, it was adversely impacting our ability to recycle water. There's a quick overview. So the pilot installation at Goleta happened very quickly. We were able to get Moleaer arranged the delivery of a self-priming pump. And so in this setup, we are actually installing after screenings and after grit, and that's to protect the pump and our technology. So we are literally pulling from a channel through a pump and back through our diffuser into the channel. So we are treating almost the entire average dry weather flow through the nanobubble generator for at least one pass. So the purpose of the installation at Goleta was to reduce the surfactant concentration. Goleta had done a lot of research and a lot of testing that correlated surfactant loading with these upsets. So for Goleta, the surfactant concentrations are very high. So there's the different types of surfactants, but ultimately it's that total concentration that is going to inhibit or diminish the efficacy of the treatment process. So for Goleta, the untreated wastewater had a total surfactant of 11.7, which per literature is above what would be expected to see. So with the nanobubble generator running, we actually did a mass balance across the primary clarifier to ensure that we were actually oxidizing these compounds into something else, and that they weren't just either going out in the primary effluent or out in the primary sludge. So this mass balance shows how many pounds of surfactants are going into the primary clarifier, or actually, sorry, this is before the nanobubble generator, how many pounds are going in and how many pounds are going out in both the effluent and the sludge. So when you think about this, you have nearly 400 pounds of surfactant coming into the treatment plant on a daily basis, which it makes sense. You go to Costco, you see those big packages of soap going out every day. So the interesting part about how surfactants work, they're trying to hold contaminants, but when they're in high concentrations, they're also trying to get out of water. So surfactants want to coat the interfaces between surfaces and water. And that's also how they coat bubbles within the wastewater treatment process, preventing their efficient oxygen transfer. This picture shows a before and after. On the left is a hydraulic equalization basin at Goleta, and you can see that the surface is almost completely covered with foam caused by the surfactants. So if you think of a natural lake or pond, if you were to stop the oxygen transfer through the surface, you would cause sepsicity and anaerobic digestion if there's solids available, but this would cause fish kills and other major problems. So by removing the surfactants, we're improving that natural oxygen transfer, keeping this equalization basin fresh, helping reduce those odors that could form. So really amazing to see on almost an instantaneous difference on our equalization basin at that plant. So for liquid solid separation, once again, surfactants are trying to use water as a solvent to pull things off that are otherwise not miscible or are hydrophobic. So the improvements with nanobubbles that we saw in the primary clarifier, once again, very instantaneous, significant odor reduction. We're seeing nice clear water from the top of the clarifier all the way down to the bottom where the sludge or the solids are accumulating. The solids are compacting well. They're not denitrifying or fermenting. So it's allowing us to hold these solids in a primary clarifier longer, concentrating them better, and that makes some of our other processes in the treatment plant more efficient. So the numbers are what we really have to depend on. So this graph looks at our removal efficiency across the primary clarifier. So in this instance, we're looking at how much of the solids are we removing. and the higher, the better. So prior to nanobubble pretreatment, we were removing about 69% of the total suspended solids to the primary clarifier, which is not a bad number. It's within what you would expect. But instantaneously after nanobubble pretreatment, we're seeing a 10% increase to 79% removal, which is considered very high for this type of technology. So the next part of that treatment process that I outlined was the biological treatment process. This is where we're using biology to add these contaminants to their biomass. In this graph, you're seeing that there's energy required to add oxygen to the process. It's actually, for most all wastewater treatment plants, it's the highest energy demand is adding oxygen to the water. Prior to nanobubble pretreatment, you can see that we were at 122 kW. Almost immediately, with reduction of surfactants and the improved oxygen transfer, we were able to reduce the energy to 95 kW. And lastly, we start to see another major swing. In wastewater treatment and in the activated sludge process, the way that we control the process is by the age of our biomass. So we actually calculate how much biomass we have in the treatment plant, and we systematically remove a portion of it to maintain a certain sludge age, and we call that sludge retention time. So each time we go through that that sludge retention time, we're theoretically renewing the biomass. So for Goleta, their SRT was 10 days. And what we saw was right at the third SRT, or 30 days into the demonstration project, there was a significant change to the biomass. So if we think of just general biology, all of us respond to our environment and we adapt to the environment. In wastewater treatment, the biomass is the same. It's going to adapt to the environmental pressures. At Goleta, the primary environmental pressure was having biology that could survive the impacts of QACs and surfactants. It wasn't necessarily the most efficient biology for the wastewater treatment process, but it could survive. What we're seeing as we get to this third SRT is that the biomass is actually now starting to convert to what is more efficient in the wastewater treatment process and less focused on surviving these surfactants. So we start to see a very consistent and healthy biomass that's more efficient. The other thing to note is that prior to nanobubble pretreatment, there are wide swings in the energy that's used. And this was caused by these periodic upsets. And so the periodic upsets, I didn't really touch on it before, are based on human nature. A lot of us, decide to do most of our house cleaning, laundry, and other things on the weekends, and specifically Sunday. So when you look at some of these upsets, they're usually falling on Sundays. So other benefits to the activated sludge is the improved settleability. Goleta's always had a really great settling sludge, and there's a lot of importance to the settleability of the sludge. Like I said, we're taking soluble contaminants from the water, adding them to biomass, and then putting that biomass into a clarifier to separate it out. So at every wastewater treatment plant, there's usually a way to contact the water with the biomass and a way to separate the biomass out. and it's done in different ways at different wastewater treatment plants, but an activated sludge aeration basin and a secondary clarifier are the most common way that we do this. So typically, the activated sludge settleability test takes 30 minutes, and that is what the measure is. The video that you're watching here is about a minute into it, and we were almost at the fully settled volume. So this is really important for a lot of wastewater treatment plants. It improves the capacity of the wastewater treatment plant when you have a fast settling sludge. Now, if sludge settles too fast or is not a quality sludge, it can lead to poor effluent water conditions, but we don't see that at Goleta. And with our technology, I think we're improving those sludge conditions immensely. So that's finishing up there. So the SVI at the end of this was about 66, which is great. This is kind of a sweet spot that we're finding in the wastewater industry for efficiency and effluent quality. Let's see. So with that, we'll look at the effluent quality improvement. One of the measures of effluent quality is biological oxygen demand and total suspended solids. So with wastewater treatment, almost every single municipal plant in the United States has an MPDS permit. And every single one of these plants will be measuring BOD and TSS. The purpose of the MPDS program was to protect the waters of the United States. And primarily the focus was on ensuring that we weren't killing fish. And so one of the measures of the effluent is biological oxygen demand. And to make sure that the water being discharged to the waterway wasn't going to consume the oxygen that the fish needed. So the treatment process itself is trying to take this BOD and transform it or accumulate it as solids. So at the beginning of this graph, we see that our BOD is considerably higher than those solids. And what that says to me in the wastewater industry is that the process isn't that efficient at converting those soluble contaminants to something that can be removed. So once again, we started on May 10th, and we have this first period of time where we start to see these two measures of water quality come together and ultimately decrease. This first part of it is likely due to that COD fractionation, or the change of slowly degradable COD to something that is readily degradable. And then this last change mimics what we saw with the improvement in the health of the bacteria in the treatment process. So once again, there's very immediate changes that we see in the wastewater treatment process, but then again, we see the biology improve, become healthier and more efficient. So another change related to both of those aspects of the pretreatment is the amount of chemical we needed to use for disinfection. So most wastewater treatment plants use chlorine bleach to disinfect their water. Chlorine bleach is very reactive and will react with organics in the water. And that's what we consider when we see an initial chlorine demand. And what that means is that we're putting in bleach and not actually getting a chlorine residual. So there are reactions happening in the water that are using up that bleach before we can even start disinfecting. Once again, we see that we start out, there's massive swings. These all correlate with the upsets that were coming into the treatment process. During this initial period, as the biology was changing, we're still seeing these large swings, but overall, the amount of chlorine needed to get a residual decreased by about 10%. As the biology became more efficient, we see the process health. For one, we see the massive swings become a lot more stable, but also we have significantly less initial chlorine demand. And that's due to removing those organics from the waste stream. So all of these things are great. And more than anything, when you start to see a more stable process, you have much happier plant managers and plant operators. So to move forward, the pilot or the demonstration pilot used a rental pump. They're definitely designed to be very flexible and be able to be deployed, but they aren't the most efficient for a long-term installation. So for Goleta, we're looking at a submersible pump in its existing channel, and we're able to decrease the energy or the horsepower of the motor considerably as we size to the need and not necessarily use a rental pump. So just a quick look at a conceptual installation at Goleta. This is actually looking down on the grit channel where we're currently pulling and discharging back to. And so we'll be able to fit a submersible pump within that channel and just recirculate with the NBG6 here at the top. So what does this all mean for Goleta? They're happy, odors are reduced, the process is more stable, but it's also important to do the right thing for the ratepayers and make sure that they're not spending money without justification. So the net reduction in energy demand came to about $32,000 a year. The reduction in sodium hypochlorite bleach and sodium bisulfite, $15,000 a year. Goleta, to help counteract the effects of the surfactants, was using bioaugmentation, which is very expensive at $44,000 a year, and they are now able to eliminate that. And then because of the improved efficiency of the process, they're actually able to remove one of their biological treatment trains that has an energy cost of $36,000 a year. So in total, there is an avoided cost of about $127,000 a year. So this is really compelling information when it comes to a sale, but also to a general manager being able to convince their board of directors to go ahead with a permanent installation.